All right. Hello, class. Uh, Ask and you shall receive. There's Hazel right there. Um, she did a big uh-oh yesterday on the rug, so she's kind of in trouble. She's an old dog, though, so I don't really hold it against her. Everyone has accidents. But when she has an uh-oh, it's a big uh-oh. And it took me a while to clean up. All right, so today I'm going to do a free response from 2012. Let me say hi to everyone who's watching. Hey Rowan, hey Zach, hey Alex, hey Rourke, hey Selma, hey Mina, hey Mo, hey Steven. So yesterday Jaden said something about maybe they're releasing practice exams or something like that. So I'm going to look into that and maybe do those tomorrow instead of what I had originally scheduled. Sorry, I'm a bit late. I was really hungry and I wanted to get some lunch first. Okay, so let's get into it. This is the 2012 free response, and we're on question 1. And it says, Experiment 1, a block of mass 0.3 kilograms is placed on a frictionless table. There's a spring. The block is set into oscillatory motion by stretching the spring and releasing the block from rest at time t equals 0. A motion detector is used to record the position of the block as it oscillates. The resulting graph of the velocity versus time is shown below. Positive direction for all quantities is to the right. Okay. Determine an equation for v of t. All right. I can see that the amplitude, let me draw so first of all, this is going to be a negative sign. So v of t is going to be negative a sine of omega t. So it's up to us to determine what is a and what is omega. And just to remind you, omega is 2 pi over the period. Okay, so I can see that the period is 0.7 seconds. So it's going to be 2 pi over 0.7. And that gives 8.98 radians per second. And then the amplitude I can see is roughly, I'm going to say, it's a little bit hard to see exactly where it is. Let me draw a horizontal line. Looks like it's about 0.16. So that means our velocity as a function of time is equal to negative 0.16 sine of 8.9 t. Part B. Given that the equilibrium position is at x equals 0, determine the equation for x of t, including numerical values for all constants. So I want to integrate that. So doing the integral is going to give, let's see, we do the integral, it's going to be x of t equals a over omega cosine of omega t plus a constant. Okay. So what is that constant going to be? Well, we know that x of 0 equals 0. So that means that it's equal. And then if we plug in 0, we get cosine of 0 is 1. So we have a over omega plus c. So that means that c equals minus a over omega. So therefore, the x of t is a over omega cosine of omega t minus 1. So what is a over omega? It's 0.16 divided by 8.98. And it is, so we get 0.018 times the quantity cosine of 8.9t minus 1. C says calculate the value of k. So k, did it give us the mass of the block? Yeah. The period is 2 pi square root of m over k for a simple harmonic motion system. So we saw that the period is 0.7, and then that equals 2 pi square root of the mass, which is 0.3 over k. So we can solve that for the stiffness, which I will do on my calculator. And we get that k is equal to roughly 24 newtons per meter. Okay, I'm guessing there's going to be experiment 2. Gosh darn it. Okay. The block and spring arrangement is now placed on a Selma asked the question, hey, Mr. P, do you know which sections are not included on this year's AP exam for E&M? I believe that Rourke posted something on the Discord that had what is on each one. So I will post again to figure that, to tell you guys what. But yeah, it's basically no magnetism. There is something on the Discord though. Hey James, nice to see you today. Okay, block and spring arrangement is now placed on a rough surface. The block is displaced so that the spring is compressed a distance d and released from rest. On the dots below that represent the block, draw and label the forces, not components, that act on the block when the spring is compressed a distance d over 2. And the block is moving in the direction indicated by each dot. Okay, so, we're going to have normal force and weight force, and both of these will have normal force and weight. So those pretty straightforward. So normal force and weight here as well. And then we've got an elastic force. Now, if you're moving towards equilibrium, you're to the left. The spring is compressed, which means that that force is going to be to the right. So this is the elastic force. And then it's a rough surface, so friction is going to be pointing opposite the direction of motion, like that. Okay. I should draw friction as shorter because it is accelerating towards the equilibrium position. Now, what if it is passed through equilibrium and it's moving away from equilibrium? Well, now the spring is instead being stretched, so it's going to pull back. Okay. Furthermore, the block is still going to the right, and so friction is still going to point to the left. Okay. So it would be something like that. Again, I haven't labeled these, so you would want to label those on an actual exam. Draw a sketch of velocity versus time in this case. Assume there is negligible change in the period and that the positive direction is still to the right. Okay? It's basically going to make this damped simple harmonic motion. So, you're going to see the typical damped simple harmonic motion. This is one period. This is two periods. So let me just maybe something like something like that. I tried my best. All right. Number 2. You are able to perform an experiment investigating the conservation of mechanical energy involving a transformation from gravitational potential energy to translational kinetic energy. You are given the equipment listed below, all the supports required to hold the equipment, and a lab table. On the list below, indicate each piece of equipment you would use by checking the box next to them. Okay. So there's a lot of different possibilities here. You're definitely going to need a meter stick because you need to know the Y value if you're going to, you know what I mean. If you're going to get gravitational potential energy, you need to know Y. I'm going to use an electronic balance. That's basically a scale. I'm going to use a set of objects of different masses and a lightweight, low friction pulley. Outline a procedure for performing the experiment. So what I would do is there's lots of different answers to this question. First of all, like now that I'm watching it, I'm oh, don't I need a? I probably need a stopwatch as well. Is that what I would do? Yeah, probably. Okay, so I did part A. So for part B, I would set up the Atwood machine. So you might recall that the Atwood machine has a pulley, and then it has two masses, 1 and 2. Okay, and let's say 1 is the heavier mass. Okay. So what I would do is my initial energy is going to be equal to 0, and that's going to be equal to the final energy, which would be, so let's suppose that this mass falls a distance of a distance d. So then the final energy is going to be m1 g times minus d. And then if this one falls a distance d, then the other one rises a distance d. So we have plus m2 g d. And then the masses are connected by a top rope. So I would need to, that means they're going to have the same speed. So there's a kinetic energy term, 1/2 m1 plus m2 times v squared. So basically I would see, my procedure would be to, see, is this equation in fact true? Okay. C, I just did part C. After your first trial, your calculations show that energy increased during the experiment. Assuming you made no mathematical errors, give a reasonable explanation for this result. One of the things that I'm seeing is that there's not really a great way to measure velocity. That's what I see. If you look at this list of things, there's really nothing that is going to allow you to measure the velocity very accurately. All you have is a meter stick and a stopwatch to measure velocity. So I would say that your velocity measurement is not going to be very accurate at all, especially because the system is going to be accelerating. So it's very possible that you could be miscalculating the velocity and it could give an increase. Okay, that's what I think is the weakness there. Or there's something else is doing work on the system that you didn't know about. Part E says, on all other trials, your calculations showed that the energy decreased during the experiment. Assuming you made no mathematical errors, give a reasonable physical explanation for the fact that the average energy you determined decreased. So I would say that friction is going to tend to take energy, and friction in the pulley. You could also talk about the fact that it's a lightweight pulley, so the pulley does have some rotational kinetic energy as it's spinning. So there's little things there. Oh, Foo's right. I didn't even choose a string for the pulley. I'm assuming that this pulley comes with strings. But yes, good catch. Okay. That was kind of a weird question. I'm going to bet this one's going to be... This is a pretty short free response, it seems like. Okay, a ring of mass m, radius r, and rotational inertia mr squared is initially sliding on a frictionless surface at a constant velocity v naught to the right. At time t equals 0, it encounters a surface with a coefficient of friction mu and begins sliding and rotating. After traveling a distance L, the ring begins rolling without sliding. Express all answers to the following in terms of MR, V naught, mu, and fundamental constants as appropriate. So A, starting from Newton's second law in either translational or rotational form as appropriate, derive a differential equation that can be used to solve for the magnitude of the following as the ring is sliding and rotating. Okay, so for I, the linear velocity has to do with Newton's second law for translation. So we have net force equals ma. Because so basically we have it's sliding. It's sliding. And so we're going to have some coefficient, some frictional force that is slowing it down. Okay? So the frictional force is going to be mu normal. Okay? And that equals m times dv dt. So that's pretty straightforward. The angular velocity as a function of time. So we're going to use net torque equals I alpha. Okay. And the net torque is friction, which would be mu mg times r equals mr squared times d omega dt. It's actually a negative torque because it's going to be a counterclockwise, or it's going to be a clockwise rotation, excuse me. Part B, derive an expression for the following as the ring is sliding and rotating. The linear velocity as a function of time. The angular velocity as a function of time. So, these are both just constants, right? So, integrating it is just going to give a factor of t. So we're just going to have minus mu gt plus a constant equals v as a function of time. And so setting time equals 0, we know that at time equals 0 it has a speed of v naught. Okay, so that means that c is equal to v naught. So we have v naught minus mu gt is equal to the velocity as a function of time. Okay. Solving the second equation gives us the r's cancel out, that cancels out. So we have minus mu g over r equals d omega dt. And integrating both sides, we get minus mu g over r times t plus a constant equals omega. Now, it starts out not spinning, so that means that c equals 0 in this case. So we have omega equals minus mu gt over r. Okay? How long does it take to travel the distance L. Well, this says that the acceleration is minus mu g. So we have which kinematic equation do I want to use? So we have delta x equals v naught t plus 1/2 at squared. The delta x is L. The v naught is initial velocity. They just called it v naught. And then the acceleration is minus mu g. So we have to solve this quadratic equation. This says 0 equals minus L plus v naught t minus mu g over 2t squared. So solving that, we get t equals negative b plus or minus the square root of b squared minus 4a c all over 2a. All right. So that says that now which of the solutions am I going to choose? We can see we have a minus here, and if I give a positive, I'm going to choose the minus solution because that is going to give us a positive amount of time. Okay, so I have t equals v naught plus square root of v naught minus 2 mu gl over mu g. All right. Derive an expression for the magnitude of the velocity of the ring immediately after it has traveled the distance L. So again, we're going to have use another kinematics equation. V final squared equals V initial squared plus 2a delta x. So that says that V final equals square root of V naught squared plus 2 times the acceleration times the delta x. E says derive an expression for the distance L. So basically what's going to happen is you can see that because it's sliding, it's actually slipping, V is not equal to omega r. So what we want to do is we want to see at what time is V equal minus omega r. Okay, now I put an extra minus sign in here because a clockwise rotation corresponds to a positive translation. So, so we're going to set V naught minus mu gt equals minus omega times r. So we have minus mu gt over r times r. Okay? So V naught equals 2 mu gt. That says that the time is, see that says that the time is v naught over 2 mu g, and then we could plug that into a kinematics equation to see how far it goes in that amount of time. So again, plugging it in for delta x. So we have v naught times v naught over 2 mu g plus 1/2 times minus mu g v naught over 2 mu g squared. And then that would be equal to L. So I'm not going to simplify it because I'm a little bit late for my next class. But that's the idea. Okay? So we're waiting until the point where this condition for rolling without slipping is satisfied, which if it is slipping, then that condition is not satisfied. Okay? So that's my lesson for today. Tomorrow I will hopefully have some examples from the new exam for 2020. I hope you guys have a great rest of the afternoon, and I will talk to you tomorrow. Bye.